Okay, welcome to another week of Math Divulged. So if you don't know who we are a group of high schoolers and some college people who have done math for a very long time. And we are releasing these lessons as a free class to just help spread competitive math and increase the skill level of its participants. So we're going to start screen sharing. Our TA for this session will be Andrew Kai. So please direct all questions to him as I cannot see the screen right now.
Yep, that's me.
All right, I'm Naveen Makat. You guys probably already know me because I've taught quite a few of these classes before. So let's get started as soon as I can find where we are. All right, today's topic is angle chasing. So if you don't know what angle chasing is, it's pretty self-explanatory. You just find a bunch of angles by using other angles. There's not really much else to describe it. Before we start with actual angle chasing, we gotta introduce a few things. So if you don't know what the centers of triangles are, there are three important centers that you need to know. The first one is called the incenter. So the incenter is a point that is equidistant from all line segments of a triangle. How do I describe that? Well, how do you drive it? Let's take a look. So you have a triangle highlighted in this yellow-orange color. And in the center, with the green line, I drew a line segment that is equidistant from these two, from this line and this line. So how do I know it's equidistant from those two? Well, if you take a random point on it, as highlighted right here, and if you draw perpendiculars from that point to the two lines, well, we know that we can actually use a congruence. We know that they share the hypotenuse and they're a right triangle. So we also know, this is actually enough information to tell us that these two triangles are congruent. So since these two triangles are congruent, that means that these two angles, are the same. Since those two triangles are the same, that means that this green line is an angle bisector. So you guys can probably guess that the incenter is going to lie on the intersection of three angle bisectors. But how do you prove that those three angle bisectors intersect at one point? How do you prove they're concurrent? Well, let's take a look at two of them. So I'm going to erase all of this and erase that one as well. Whoops. So let's draw our second angle bisector, which is about this much, I believe. Let me just draw that. So we know that two lines intersect at some point over here, and we're gonna highlight that in purple. So how do we prove that this third line intersects to that point? Well, let's take a look at what both lines mean. We know that this line is where this line and this line, it's equidistant from these two lines. This line over here is equidistant from these two lines. So if a line is equidistant from if a point is equidistant from these two, but it's also equidistant from these two, therefore that point must be also equidistant to these two. And we can draw another line to show that, which is also an angle bisector. And know that that line has to pass through that point. Let me just draw that here. And there we go, that's our incenter. Another thing you can do with this incenter is you can actually draw a circle with this point at the center of the circle that roughly passes through all the point. Okay, the circle is kind of a bad drawing. Let's see if we can make it better. There we go. The circle is tangent to all three sides of the triangle. How do we know this? It's equidistant from all three sides. So therefore, all three sides must be at the same distance from the center, which is what a circle does. And another thing to notice, where it is tangent, you can actually draw a perpendicular here. Oops, I'm going to use the line tool. You can actually draw these perpendiculars, which do come in useful a couple of times. In some cases, like with this one, where the triangle is roughly isosceles, the angle bisector and the radius of the circle may overlap. Let's move on to the next one, the centroid. A centroid occurs when we have three medians. Now, what medians do is that they divide a segment into two equal parts, like so. Drawing's not going to be perfect, but it's satisfactory. Now, these also converge at a single point. They are concurrent. And this is the centroid. So proving that this one is also concurrent is significantly harder than the other two centers that we'll deal with, but it is doable. So what we're going to do is we have this triangle. First, we label our points, A, B, C. We'll label these D, E, and F, and our centroid by convention is typically called G. So how to prove that they are concurrent? We're going to form this line EF or FE, whichever one you prefer. Let's use a different color for that. There we go. Now, next thing we do, we're going to notice that we notice something very interesting. FE is a mid segment of triangle ABC. How do we know this? Let's draw out this. We know that these two are the same. We know that these two are the same. We know that these two are the same. So AF is half of AB, AE is half of AC. Now FE connects the midpoints of two sides of a triangle. And we notice that AFE and ABC are similar triangles. Therefore, FE is parallel to BC. Now that we know this, we know that angle EFG, another color here, let's use light red or orange, whichever one that is. This angle is congruent to this angle. This angle is congruent to this angle. Therefore, triangle EFG and triangle BCG, they are similar because they share all the angles. Since they're similar, their sides are proportional. So this means that, another color, let's use white, EG over GB is equal to FE over BC, which is equal to 1/2, because we proved that FE is half of BC. And this means that 2EG is equal to GB, and EG is equal to 1/3 of EB. Whoops. If you're confused where that last thing came from, if this is x, we know that this is 2x, so therefore EG is 1/3 of EB, x over 3x. This also means that BG is 2/3 of EB. What does this mean? This means that, well, we know that EB is our median and BG is our vertex to the median. So the median actually exists at a point where this is 2x, this is x. The same thing applies for all the other medians. This is 2y, this is y, this is 2z, this is z. That barely looks like a y. Yes. So take that a minute. Since we know that all these three intersect at the same point, hold on, my mom's calling. We're gonna take a break for a second. All right, we're back. So what I was saying was that if we were to look at D, and if we didn't know that AD passed through point G, we know that AD is a median, and we know that it must be cut 2/3 of the way, since we can do this with any other median, right? Since we know that this point is G, that means AD must intersect at point G. So that therefore, all three medians intersect at the same point, which is the centroid. Let's move on to the next center. This center is a bit harder to visualize. It's called the orthocenter. So the orthocenter happens when you draw the perpendicular bisectors of all the sides. So let's do that. There's three cases. We have the acute case, we have the right triangle case, and the obtuse triangle case. And we'll see why those are different in a minute. So let's draw this. So over here, what you see is that all three perpendicular bisectors intersect at the same point again. And this is your orthocenter. Now, why do they intersect? Well, it's the same story as our incenter. A perpendicular bisector is equidistant from two vertices this time. So this line right here is going to be equidistant from this vertex, it's not drawing, this vertex and this vertex, this line over here is going to be equidistant from this vertex and this vertex. So just like the incenter, there's a point where we are equidistant from all three. And that is our orthocenter. So what does that mean? Because normally when we have equidistant points, you can draw a circle, right? If we're equidistant from all three vertices, we can draw a circle with the center at the orthocenter that goes through all three vertices of the triangle. Let's just sketch that out real quick. And this is your circumcenter. So before the incenter was a circle inside the triangle, the circumcenter is a circle outside the triangle. You can always draw a circumcircle for any triangle. So in the case of the acute triangle, the circumcenter is inside the triangle. This is not always the case. If you go to the right triangle, let's draw our perpendicular bisectors for this. This is a very different case. In this case, they actually intersect at the midpoint of the hypotenuse. They intersect right here. What this means is you can draw a circle that has the hypotenuse as the diameter. Passes through all three. Just like before. This also means you can draw a line here. Let's change the color of these three. And what you'll see is that these three line segments are congruent, which means you have a lot of isosceles triangles to work with. For example, this and this, or this and this. This occurs in a lot of AMC problems in particular. We see this all the time. And in this case, the orthocenter is on the triangle. Let me see. Is everyone getting this so far? Andrew, is there anything you want to say?
Naveen, I think you got all the points on the nail.
All right, seems good. Actually, that is not true. This is not the orthocenter. This is the circumcenter. Someone just caught that. Yeah. Yeah, orthocenter is something completely different. Yeah, this is the circumcenter, not the orthocenter. Have to create a new slide now. So in this case, the circumcenter is on the hypotenuse of the triangle, on the midpoint in particular. For an obtuse triangle, this is not the case. This is a very different case. The circumcenter is actually going to be outside the triangle. There we go. All three are perpendicular bisectors and they're going to intersect at one point. And we can also draw a circle This is a lot harder to draw. Close enough. Yeah. So again, all 3 points can be shown to have a circle that goes through all 3 points. And in case of an acute triangle, the circumcenter is inside. In case of a right triangle, it is on the midpoint of the hypotenuse. And in case of the obtuse triangle, it is outside the triangle. So as we mentioned earlier, we do have another center that we need to cover. So I'm just going to erase this in-center thing. We might as well cover the orthocenter while we're at it. So the orthocenter, can't believe I confused that. Let me just cleanly erase everything. This is where the altitudes are the same. They intersect at the same point. So if we draw the altitudes and not the perpendicular bisectors, they will also intersect at the same point. There we go. So we get a bunch of right angles we can work with. So this is true for both orthocenter and circumcenter. You get a lot of right angles, which makes angle chasing very nice. So to prove that we need sorry guys, my dad is actually sick right now, so if my mom calls me, I kind of have to disappear for a couple seconds in case something happens. So we're not gonna, since we're running out of time, we're not gonna prove that the orthocenter is concurrent. We'll leave that as an exercise because there's some problems that we want to get to. So this is from 1999 AMC 8 number 21. So what we're gonna have is we have this angle over here is equal to 100 degrees. This angle over here is equal to 110 degrees. And this angle is equal to 40 degrees. So our objective is to find this angle over here, angle theta. I'll give you guys about a minute to work it out. This isn't like too hard. It is on an AMC 8 after all. All right, now that we're done with that, we are going to take a look at the problem. So one particular tip that comes useful when you're angle chasing is you want to find a triangle that the angle belongs to and find the other angles of that triangle, because the triangle's angles sum to 180. And we'll go over a proof for that very shortly. So let's look over here. We want to find this angle first, which isn't too hard to find. That angle is going to be 180 minus 100. So this is 80 degrees. And we want to find this angle. And to do that, we know that this angle is the same as this angle. Now, how would we find that angle? Well, we want to find it, well, we look at this triangle right here. This triangle. And we know that we need to find this angle now. That angle is going to be 180 minus 110, which is equal to 70. And now if you look at this angle over here, we know that this is going to be 180 minus 40 minus 70, which is equal to 70 degrees, purely by coincidence. Therefore, this angle is 70 degrees. So angle theta is equal to 180 minus 80 minus 70 is equal to 30 degrees. This is pretty straightforward. We're going to look at a proof that the angles of a triangle actually do sum to 180, just for the sake of rigor. So here's a triangle. I've labeled the angles red, green, and blue. So what we're going to do is we're going to draw a line that is parallel to this segment over here. So let's do that. So now what we have are a couple angles that are missing. So this angle over here is going to be the same as this angle. So we can draw that. This angle over here is the same as this angle. So we can draw that. And we're looking for the sum of the three angles. So green plus red plus blue is equal to 180. So that's just a quick proof. Going back to our regularly scheduled programming. Let's take a look at an AMC 12 problem, number 6 from 2007. So triangle ABC and triangle ADC are isosceles, with AB equals BC and AD equals DC. D is inside triangle ABC. Angle ABC equals 40 degrees, and angle ADC equals 140 degrees. So what is angle BAD? Give you some time to look on that. All right, let's take a look at this. So one feature of an isosceles triangle is that if you know, if you know one angle, pretend that's isosceles. If you know this angle, we know that these two angles are going to be the same, and we know what their measures will be. So let's take a look at triangle. Let's take a look at this angle, this green angle that I've highlighted. What is this green angle composed of? Well, we know that it's going to be this. I can't use a good color for this one. It's going to be angle BAC minus angle, this drawing is not good, minus angle DAC, which is over here. So let's find these two angles. Angle DAC, we know that DAC is equal to DCA. Why does this thing keep moving? And we know that since these two angles are the same and the other angle is 140, we know that if we call it angle X, so 2x plus 140 is equal to 180. So X equals 20. So angle DAC is equal to 20 degrees. On the other side, we have angle BAC, this big angle. And we know we can do the same thing here. Let's call it y. So 2y plus 40 is equal to 180 because of the big triangle BAC. So y is equal to 70 degrees. Let's add some things here. So angle BAC is equal to 70 degrees. And we know that we're looking for angle BAC minus angle DAC. So 70 minus 20 is equal to 50 degrees. So that's another tip of angle chasing. Try to find out what angles compose the angle that you're looking for. Let's look at a slightly harder problem. We have problem 2010 AMC 12A number 8. So the hardest part about this one for me was drawing the actual diagram because the problem is quite vague on details. We have that AB, the length of AB is 2 times the length of AC. We let D and E be on segments AB and BC respectively, such that angle BAE is equal to angle ACD. Let F be the intersection of segments AE and CD, and suppose that triangle CFE is equilateral. What is ACB? And someone asked me to give the diagram. The whole point of this question was to not give the diagram because that is one of the harder parts of actually doing this. So we're going to construct the diagram as we go. So try to make the diagram by yourself for a bit. Some tips that I'd use on the AME, use some colored pencils. You are allowed colored pencils last time I took the AME. And these help highlight different lines, different segments. They make things a lot less confusing. All right, so what do we know for sure about this diagram? Well, there's not much that we know. There's no concrete information except for the fact that triangle CFE is an equilateral triangle. So let's draw that equilateral triangle. It's not much of an equilateral triangle, but it works. Just ignore that little segment at the end. What else do we know? We know that AB is equal to 2 times AC. We also know that we have a bunch of 60-degree angles here, so let's mark those all down. These are all 60. We know that angle BAE is equal to angle ACD. So when we label this, we're going to have a point like B over here and a point A over here. And this angle, let's actually draw the entire thing out now. It's going to look something like this. When it comes to geometry problems, drawing a good diagram is one of the hardest parts. Especially when you get to Olympiad level stuff, then things become ridiculously complicated. So use compasses and protractors if you don't have those. So what do we know? We know that if we label this point B, label this point A, we know this is going to be D because it says that D lies on AB. It says that angle BAE, does that intersect? Not quite. So another thing I'm going to highlight is that these can take a couple of attempts to draw. If you don't get a good diagram and things start to break, then don't be afraid to draw a new one. So here's a marginally improved one. All right, that's significantly better. It took a couple tries, but that's honestly the hardest part of the problem. So now we can move on to actual angle chasing. So label this point F again. So we want to find, we know that these two angles are the same. It says that angle BAE is equal to angle ACD. And we know that CFE is equilateral. We want to find ACB. So we want to find green plus 60 degrees. So let's actually label that. So we're going to call a green thing X because variables assign a nice name to things. Let's call this X. So we know that angle EAC plus angle FCA plus angle ECF plus angle AEC is going to equal 180. So let's label that. Angle EAC plus angle FCA plus angle ECF plus angle AEC. This should make sense to you. This is triangle ACE. These all sum to 180 degrees. So let's look at that. So let me just write that down. Triangle EAC plus FCA plus ECF plus AEC. And we can rewrite this in terms of X and 60 degrees. Angle EAC, we don't really know, so we'll keep that. Angle FCA, we know that this is the X. Angle ECF, we know that's 60 degrees. Angle AEC is also equal to 60 degrees. It's all equals to 180 because it's a triangle. It adds to 180. 10% remaining, okay. So therefore, angle EAC is equal to 60 degrees minus X So remember, we wanted to find angle ACB. So angle BAC, which is this angle right here, that is equal to angle, let's write that over here. Angle, get out of my face, BAC is equal to angle EAC plus angle BAE, which is equal, if you take a look at this, to 60 minus X, because we know what angle EAC is. And then angle BAE is equal to X, because it's highlighted in green. So angle BAC is equal to 60 degrees. So we can write that over here. This is also 60. Now, if we look at the information that we've used, we've left out something very critical. We have not used the fact that AB is equal to 2 times AC. However, we know that this is X, let's call it A, this is 2A, and we know the angle in between. This is an SAS triangle. If you have a 1:2 ratio and an angle of 60 degrees, that means you have a 30, 60, 90 triangle. So that means that this angle is 30, but more importantly, this is a right angle. Triangle ACB is a right angle, is a right triangle. So the one we wanted to find was angle ACB, which is 90 degrees. So angle chasing also involves a lot of algebra at some points. Take a look at what Andrew said. If anyone asked him any questions, please send them over again because his Wi-Fi crashed. So the lesson to be learned from this problem is that angle chasing can be very algebraic at points. So you want to find things that might cancel out. You also might want to use some trig at some points. Like in this case, we found 30, 60, 90 triangles to be useful. So while I get my charger, because this iPad is about to die, it's at 9% as you can see, I'm going to show you the next problem. So you can work on that while I find a charger. So we know that we have a rectangle here, rectangle ABCD. BC is equal to 3. CD is equal to 6. And the last information is that point M is on AB such that angle AMD is equal to angle CMD. So what is the degree measure of angle AMD, which is the yellow angle? While I find a charger and check on my dad, you guys can work on that problem. Absolutely no one needs to see that, so let's not. All right, I think we're good now. All right, we're back. So if you guys have not seen the problem, here's a chance to look at it. All right, let's solve it. So there are ways to do it with trigonometry and stuff like Pythagorean theorem and law of cosines, but that really is not necessary for this problem. So Since we know that AB and CD are parallel, that means that angle MDC is also a member of the yellow angle family. So if you look over here at triangle CMD, we now have an isosceles triangle. So let's just mark that down. This is 6. So now we know that MC is 6. We notice that BMC is a 30, 60, 90 triangle yet again, because this is the right triangle over here. So we have a 1:2 ratio again. So therefore, angle BMC is equal to 30 degrees. So if we let this yellow angle be x, then 2x plus 30 is equal to 180 degrees. Therefore, x is equal to 75. And this was choice E. This is from 2011 AMC 10B, problem number 18. So we're getting significantly harder. Next problem is problem number 24. So this is significantly harder. So the information that we're given is that we have a quadrilateral. So we have ABCD. AB is congruent to BC, and this is equal to CD. Angle ABC is 70 degrees, and angle BCD is equal to 170 degrees. And we want to find this angle over here. We want to find angle bad. This one's significantly harder. This should take about, like, if you're really good at this, probably take a couple minutes. All right, that was a decent amount of time. So let's take a look at this. This solution is quite hard to see. So what we're going to do is we're actually going to draw the angle bisectors of angle B and angle C. So let's do that. Let's clear out the information over here. Let's draw the bisectors. This looks more something like this, I think. So here we go. So that's not accurate then. I'm going to draw angle B first. So if you drew this right, like if you drew with a protractor and everything, you should get that these two intersect on AD. But how would we prove that? Well, obviously we know that they have to intersect somewhere, and we're going to call that point P. Now what we need to do is prove that P is on segment AD. So we notice that angle APB and CPB are congruent. And this is because they share a side, and they share these two sides, they're congruent, and they share the angles because it's an angle bisector. So therefore, we have triangle ABP is equal to triangle CBP. For the same reason, we find out that triangles CBP and CDP are congruent. It's the same logic. So triangle CBP is should have the congruent mark instead of equals. There we go. So let's draw out the angles. If you don't remember what the angles are, this entire thing was 70 degrees. So when you break it up into two pieces, it's obviously going to be 70 divided by 2, or 35 degrees. Angle BCD was 170, so divide that by 2, you get 85. So angle ABP equals angle CBP equals 35 degrees. So CP is we know that APB is equal to BPC. So let's write that down. These two are the same. And this is also equal to CPD because these two triangles are all congruent. So what we got from this result over here was that all three triangles are congruent. So this triangle is congruent with this triangle. Whoops, that was unfortunate. Is congruent with this triangle, is congruent with this triangle. That should make sense to you guys, right? So angle APB, so these three angles are going to be the same, right? Therefore, all of them are 60 degrees because they're all the same and they add up to 180. You could also get that from looking at the triangle over here and seeing that there's 85 degrees and 35 degrees. That's also entirely possible. But we notice that this angle over here is going to be the same as this angle over here because we know they're congruent triangles. So we actually didn't even need this 60 degrees to begin with. So we can actually erase that. Erasing is very hard on this app. So what I was saying, seriously? Okay, this angle are the same because all three angles are congruent. Therefore, angle A is equal to 85 degrees. And this was choice C on the actual test. Andrew, is there anything else you want me to cover? Because these are all the problems that we've done, I think.
I guess we're good because it's already 4 o'clock.
All right. So thanks for coming, guys. I'm gonna drop a link if I can. Well, in the Discord, I will send something as well. There's Luke wrote a handout on cyclic quadrilaterals, which we did not have the time to cover for this. So in case you guys have not joined the Discord yet, check that out. Link will be dropped in about 5 seconds, hopefully, when I find it. All right, that should be in all chat right about now. So join that Discord. The link to the geometry for the cyclic quadrilaterals handout will be written by Luke, and it will be there. So thank you all for coming. Have a good day, and we will see you all on Wednesday.